Internet of Things. So the market of those devices by 2030, Cisco, according to Cisco, it's about 500 billion devices will be connected to the internet. So all these devices basically need off-chip electrochemical energy storage device at this moment. Basically, it's batteries and capacitors. So those batteries and capacitors can add on a large portion or volume brightness to the whole system. So, at the meantime, we're trying to scale down the system, scale down all these devices. But at the meantime, those batteries, capacitors are still bulky. And we look into all these issues. What's first the power requirement and the energy requirement for those devices? And can we further develop on chip level or miniaturized energy and power energy storage devices to power those Internet of Things devices? So I give a few examples you can see. Most Internet of Things will need several microwatt to hundreds of milliwatt. And the energy is in the range of several hundreds of microwatt hour to several milliwatt hour. So depending on the complexity of the sense, the quality and the speed of signal transmissions and all this, noise canceling, data acquisition, the power consumption of the individual sensor node is around 1 to 20 microwatt. But if you add complexity, for example, for implantable device, the power could be in the level of microwatt to milliwatt. And I give you an example here for cardiac defibrillators. It's about 30 to 100 microwatt. And neuron stimulator is about 30 microwatt. And the drug pump is about 100 microwatt to even 2 milliwatt, depends on volume, how much drug you want to deliver. And if you add all other components, for example, you add more sensors, add a timer, and RF wake-up receiver, RF transmitter, all this, if you add up, you could consume about 600 microwatt. So those are power and energy consumption we are trying to deliver, right? So can we just simply reduce the size of current, let's say, battery or capacitors to the footprint area at about several millimeter square, less than 1 centimeter square footprint area? If we simply reduce the size of a current battery, we can't actually deliver enough power or energy. So what's the solution, right? So we have to find a solution to look back from the design, manufacturer, and architectural point of view, how we can deliver enough power or energy at a limited footprint area. So for miniaturized on-chip electrochemical energy storage system, the wish list, we hope it's small and compact. So small means the footprint area is several millimeter square, less than 1 centimeter square. The high capacity and the high power capability is the number one requirement. And we have to have a good cycle performance for long-term operation. And ideally, all this on-chip level device has to be built in a way we can integrate semiconductor processing, semiconductor, CMOS, other device to this process. So compatibility with semiconductor processing is also a key. So when we talk about semiconductor, we use the silicon wafer. Either on the wafer, we have a silicon nitride, oxide, we do different processings. So for the battery manufacturer is a totally different manufacturer sector, right? So if you look at typical batteries to power your cell phone, power your computer, just regular batteries, a battery. Those batteries actually had, if you open up the package, you can see it's basically a 2D character. So it's a layer by layer construction. So the battery will have anode, cathode, in between there's a separator and the electrolyte. So you basically put all this layer by layer structure stacked or spiral wound or folded together, put into a battery cell. So can we further scale down this process? So basically, the answer is no, we can't, because now we are dealing with a silicon substrate. How to make the high current, high power, and high energy density electrochemical device on the silicon substrate by the 2D layer by layer structure. Basically, the only way is you can deposit layer by layer, but all those layer by layer structural device has limited power and energy. So if you look at the figure at the right hand corner, so basically how to do the on-chip level structure. There's a couple of designs. First design is basically interdigital array structure. Interdigital array structure is still 2D electrode arrays, but the anode cathode can be on same plane. So not like you stack anode cathode thin film structure. So you can still try to build a electrochemical device on the same silicon substrate. So by 2D interdigital array system. And another design is three-dimensional structure. So 3D can give you more surface area and volume because it takes advantage of the vertical dimension. And another design is a symmetric or a symmetric supercap. You know, basically in this case, in this figure, it's a layer by layer structure. So when we look at all these issues, we first work on the micro battery many years ago when I was in UC Irvine working with Professor Madhu. So we first tackle this problem. We developed first 3D battery based on the carbon map structure. So why 3D concept? So let's give you a very quick, simple calculation. We borrow this slide from Bruce Down in UCLA. So this slide basically tells you very simple mathematics. So we assume we have a thin film design, 2D battery design, compared to 3D battery design at same footprint area. So it's 1 centimeter square in this case. And we assume the electrode thickness is 22.5 micrometer, and the electrolyte thickness is about 5 micrometer. And then we can calculate the total volume. So this thickness is the typical electrode thickness even for the typical batteries, the bulky batteries. So we assume we just simply scale down onto a 2D battery. So then we compare with a 3D battery. In this case, the electrode diameter is 22.5 micron. And the distance in between the two electrodes, basically, we hope we can put the electrolyte fully occupy those empty space. So the distance between the two electrodes is 5 micron. But here we assume we can build high aspect ratio electrode arrays. And the different colors shows one is the anode, one is the cathode. So we assume all these electrodes can be individually addressed, connected to the current collector. Let's say we have an aspect ratio of each rod is 50:1. So that means the height to the diameter is 50:1. So if you compare these two designs, we found out the capacity of the 3D battery is 3.5 times higher than the 2D battery. And the surface area of a 3D battery is even more, 35 times higher. So this is just a very simple concept. So when Bruce Dang reached to us, to UC Irvine Madhu Group, at that time we were working on 3D carbon maps. So what is a carbon maps? In last lecture, Professor Madhu already addressed all these carbon maps procedures. So basically, the carbon maps technique we developed use a photoresist. We can use either positive photoresist or negative photoresist. And we use photolithography processing and combined with the carbonization process. Here, the carbonization process, also called pyrolysis, is basically you put the patterned polymer patterns into the furnace. And in this furnace, we try to avoid oxygen. So we have to either use vacuum furnace or we can fill in the foaming gas or nitrogen gas. So we try to avoid oxygen in the furnace, then we can carbonize the polymer patterns to the carbon. So this carbon basically is a glassy carbon. So you can see if we use SU8, this very unique negative photoresist, we can actually build the high aspect ratio carbon lamps and the aspect ratio. In this case, we can build easily 20:1 to 50:1 aspect ratio. So I just show you some of the pictures when we work in UC Irvine. We made the first generation 3D batteries, and we also made those glassy carbon table, suspended nanowire by changing the ramping speed. If you want to do the carbonization fast, basically, you raise the temperature quicker than the normal recipe. You can also get the very porous carbon structures. For example, this picture just shows the porous carbon. Basically, during the degassing process, carbonization process, there's gas get out of this solid photoresist and turned to carbon. Then you see all these porosities on the surface. And by adding catalyst, we can also deposit nanomaterials, one-dimensional nanomaterials or two-dimensional nanomaterials on this solid glassy carbon post. So those are just typical carbon MEMS process. So how we made the first generation 3D battery? Because this is our motivation for our future work in FIU. Actually, we develop different generations of on-chip capacitors. But the main driving force for us to move to microcapacitors is because when we look at the first generation batteries, in this case, in these batteries, 3D micro batteries, we have two sets of electrodes. One is a bare carbon, glassy carbon. So you can see the diameter of this carbon is much smaller than the very broad holes. Those are polypyrrole. So those are polypyrrole coated on the bare carbon post. So we basically use electrochemical polymerization method to deposit polypyrrole on one set of the bare carbon post. Then we create anode and the cathode. Carbon is the anode and the polypyrrole is a conductive polymer. We can use it as a cathode. It's not the best battery setup, but because the simplicity of electrochemical deposition, we can deposit conductive polymer very easily on the carbon post. So we adopt this recipe. And we found out polypyrrole, even it's not the best cathode material, we can discharge lithium ion into the polypyrrole. Basically, this material, if you look at the thin film polypyrrole material, we can light up LED if we just check out the half cell. So we adopt this polypyrrole and carbon as a first generation 3D micro battery structure. Then we did all these studies about the half cell performance and the full cell performance. And we found out this is not a good battery. Absolutely, if you look at the charge discharge curve, it's not like a typical battery. For the anode side, the glass carbon can deliver okay performance, let's say 220 milliampere hour per gram. That's a specific capacity, per gram. And if you look at the aero capacity, we can deliver 93.1 microampere hour per centimeter square. Compared to graphite, it's only, let's say, 2/3 of the performance compared to graphite because we're using hard glass carbon and it's amorphous carbon. So the performance is not as good as graphite, but for demonstration of our first prototype, it's good enough. So we still look at the half cell performance here for the 3D polypyrrole. You can see it at 53 milliampere hour per gram. So it's almost 4 times difference. That's why when we deposit polypyrrole, if you look at the first picture, the volume is tuned to try to match with the total capacity of the carbon. So we have to make almost 4 times higher weight. Then you look at the volume, it's almost like polypyrrole has to be doubled. But when we look at a full cell, we charge a carbon first, then we remove the lithium metal, then let the cell carbon with the lithium ion inside this carbon, then do the discharge process with a counter electrode as a polypyrrole. Now we found out the performance is really bad. How bad is it? If you look at the area capacity, because it's hard to estimate the total weight, it's on chip level, already on silicon wafer. So we found out the area capacity, ideally, by the calculation, we assume it's 43.5 microampere hour per centimeter square, but in reality, we only get 10.6 microampere hour per centimeter square. What's the reason? If you look at this structure, you can see majority of the space will be just electrolyte. You can't really make this 3D battery very close. Once you want to make it very dense, there's 2 issues. The anode and the cathode can touch to each other, then you short the whole device. And we try to keep the volume as much as we can, all the active materials, but still you have a majority space will be just electrolyte. So we don't have enough active materials in this case. And the secondary, carbon is not the best electrode current collector because there's a resistance for carbon, especially when you scale up, make a high aspect ratio electrode. And another thing is the leak current. So we can see when you do the carbonization, basically the carbonization process is degassing, then redeposit some of the carbon onto a silicon wafer. So in this case, we have the silicon oxide as the buffer layer between silicon and the photoresist layer. But after carbonization, there's always some residue redeposit on the carbon, on the silicon dioxide. Even we try to do the plasma treatment cleaning, there's still leak current. So all these issues tells us this may be the main reasons for the poor performance of our first generation 3D batteries. So then we were thinking, okay, if you want to further use this structure, 3D carbon structure, as a electrochemical energy storage device, maybe the best way to do it is not make it very complicated. You have to deposit polypyrrole. That's another complexity if you do the, wet processing. And then you have to do all this cleaning. So the simple case for us to look into is actually a capacitor, micro supercapacitor. So what is a micro supercapacitor? So supercapacitor is an electrochemical capacitor. So compared to typical aluminum electrolytic capacitor, this electrochemical capacitor have actually much higher, almost like a twofold higher energy density compared to the electrolytic capacitor. And this capacitor has, at least people usually talk about two mechanisms. One is the double layer capacitor, another is a pseudo capacitor, but in between there's hybrid capacitors. So the double layer capacitor basically utilize the electrolytic charge stored at a double layer between the electrode and the electrolyte interface. And the pseudo capacitor basically is a capacitor stored charge based on redox reaction at the subsurface. So very thin layer between the electrode and electrolyte. And it's a fast charge transfer. So these two types of capacitors, you can use either mechanism to build your capacitors, or you can even make a hybrid capacitor, either hybrid by double layer electrode and pseudo capacitor electrode, or you can even make a hybrid battery and capacitor hybrid. Basically, you can use a double layer capacitor material paired with a lithium-ion battery electrode. So for my case, this is a simple version. So I didn't put all these basics slides there. But then you can see we have different generations microcapacitors on silicon substrate. So first generation is just as fabricated carbon MEMS, electrode-based on chip level capacitors. And the second generation, we have the electrochemically activated carbon electrode. Then you can see third generation, we integrate CNT on the carbon electrode. We can also integrate polypyrrole on the carbon electrode. And the magnesium oxide-based carbon MEMS electrode is a composite electrode. We can actually add more materials on the carbon pillar arrays. So by integrate pseudo-capacitor materials like polypyrrole, magnesium oxide, and the tin oxide, and also the composite materials, we can make the pseudo-capacitors on chip level. And the last category here, I will just talk to you about our reduced graphene and the CNT composite. Those are very promising materials we have been working on for almost a decade on graphene-based supercapacitors. Just quickly, the performance, just bare carbon, we have almost 0.03 Faraday per gram and equivalent to 0.07 millifarad per centimeter square. But if you activated this carbon MEMS, you can have 30 Faraday per gram. So you can see it's 100 times higher performance. And if you add CNT compared to activated carbon materials, we have a similar performance. But if you add the pseudo-capacitor materials on the carbon MEMS array, we have much better performance. So I will just quickly give you some examples. And the picture here shows our goal is make the high surface area electrode. So by adding different materials, we can try to improve the surface area, because surface area will be the key factor for the power density. And the aspect ratio and the total volume of your carbon materials will be the key factor for the total energy storage, capability for batteries, but for the capacitors, we care more about the surface area because we care more about the power density for this device. And we also have different research try to modify carbon nanotube. For example, the picture here shows, carbon nanotube can be grown directly on the carbon micropillars by two different methods. One method actually we mix with a catalyst. So in middle group, we mix iron particles into the photoresist. During the carbonization, we see this redeposition of the carbon species as a one-dimensional material onto the glassy carbon. So we have the high surface area carbon post coated with these carbon fibers. But if we coat directly catalyst on the glassy carbon post, not during the carbonization process, it's after carbonization, if you coat the catalyst particle directly on the glassy carbon, then we can put this carbon post with the catalyst into the CVD chamber. We can grow carbon nanotubes directly on the carbon post. And another research is, you can see at the bottom, A, B, C, D, those four figures, we actually can add magnesium oxide nanoparticles directly into the carbon nanotube. So that's a composite. We have both double layer capacitor based on carbon nanotube and the magnesium oxide-based pseudocapacitor material inside the carbon nanotube. And it's very well nano-confined because they are inside the carbon nanotubes. So I will just quickly show you several examples. So the performance we summarized, if we add carbon nanotubes directly on the carbon post, the performance can be 100 times higher than the bare carbon mass. So from the CV curves, you can see the bare carbon, the blank carbon mass without any treatment, it has a very small area. So the current density is low. But if you add carbon nanotubes, we grow carbon nanotubes 30 minutes up to 120 minutes. This ESD time is a time we use to coat the catalyst particles. So we have more catalyst particles if we use 120 minutes coating time. Then we compare all these materials with the carbon nanotubes on the carbon post. We found out majority materials have a similar performance. Gradually, they're increasing when you have more carbon nanotubes on the bare carbon surface. We can also treat this carbon nanotube with oxygen plasma to add functional groups. So by adding functional groups, you can see from the charge-discharge curve, without oxygen plasma treatment and with oxygen plus treatment, the specific capacitance in this case, Faraday per gram, we can almost double at the first cycle immediately after the treatment by oxygen plasma. You can increase the specific capacitance from about 35 to up to 60. But gradually, when you do the charge-discharge, these functional groups are now less stable. So you can see after 1,000 cycles, the carbon nanotube and the CMEMS-based setup, actually, the performance is reducing. So the specific capacitance after 1,000 cycles dropped to about 40 Faraday per gram. So the conclusion is oxygen plasma treatment can produce oxygen functional groups on the surface and the melee carboxylic group and other oxygen-based functional groups, which can increase the specific capacitance, but the performance, the cyclability is not good. So that's one research. And another research I want to address is we can add magnesium oxide nanoparticles inside the carbon nanotube to actually create composite materials with a nano-confinement effect. Because this carbon nanotube we use here is purchased from the commercial company. And it's about I guess about 20 nanometer diameter. And the inner diameter is about 10. If you can put magnesium oxide particle like what we did, what we achieved, so those nanoparticles has a really uniform size because it's confined by the inner diameter of carbon nanotubes. So we made two types of composites. One is magnesium oxide confined inside the nanotube. Another is magnesium oxide particles just deposit outside nanotube. So we compare these two composites. We found out we also can have a control samples, basically the closed tips carbon nanotube. That's the commercial products. Then we can also open the tips of carbon nanotubes. The goal is after you open both tips, you can put the magnesium oxide, the precursor inside the carbon nanotube. Then you can do the decomposition, then create this magnesium oxide inside the carbon nanotube composite. So you can see for the closed tip nanotubes without any treatment, we only get 25 Faraday per gram. And that's from the CV, from the cyclic voltammetry results. So you can see the black line in the CV curve. This is the closed tip carbon nanotube. And if we open the tips, then we have the, more electrolyte can penetrate into the carbon nanotube. Then we have a little bit increase of the specific capacitance up to 37 Faraday per gram. So the magnesium oxide particles we synthesize basically just chemical decomposition of the precursor solutions. So those magnesium oxide particles, we have pretty low capacitance. In this case, only 13 without any optimization. But when we put same materials inside the carbon nanotube, the specific capacitance is up to 225 Faraday per gram. And compared to another control sample, the particle is outside the carbon nanotube. The performance is only 144 Faraday per gram. So you can see the performance has a dramatic increase compared to the just single phase magnesium oxide particle. Compared to pure CNT, we have a huge increase of capacities. So the increase of capacitance can be also seen from after we normalize by just eliminate the magnesium, the CNT contribution. We can see the normalized just by magnesium oxide, the capacity could be over 1,250 Faraday per gram. It's much higher than theoretical or best performance of other people's magnesium oxide work. So we try to understand what's happening in this case. We found out when the magnesium oxide is inside the carbon nanotube, we have a magnesium 3 and magnesium 4 redox couple created. But if we have the magnesium oxide only deposit outside the tube, we only see the magnesium 4. So the redox couple plays a big role, and another contribution is from the nano confinement, because in this case, the distance between the particles inside the nanotube, between the particles and the inner wall of nanotube, that gap is much less than, could be less than 1 nanometer. So then the nano confinement can play dramatic influence for this composite. So that's a work from the SEM and the SRD. We can see, the magnesium oxide particles inside the carbon nanotube actually has both magnesium 3 and magnesium 4 redox couples. So another work I want to just give you a brief introduction is graphene CNT. So graphene CNT is a material we have been working on. So the first work for graphene CNT work was done by my first PhD student, Majid. And he basically made the just on-chip level, two-dimensional, interdigital array, so two-dimensional system. And this system, we basically use titanium gold as a current collector, and we use SU8 to deposit, as in this case, SU8 is just a mask, shadow mask. Then we can actually deposit graphene CNT composite directly by electrostatic spray deposition on the entire wafer, then try to do the lift off process. Then what we found out is this RGO CNT composite compared to pure CNT or pure RGO has a much better performance. So you can see the system is pretty small. It's about 3 millimeter by 3 millimeter size. And what we get, the performance is amazing. So we have a different CV curves here compared to 10% CNT and 20% CNT with RGO composite. You can see the pure RGO, pure CNT performance, especially from the last figure, figure 5. So the first 5 figures are at a different scan rate from 1 volt per second all the way to 50 volt per second. But for typical supercapacitor, thin film-based supercapacitor measurement, people goes to maybe 25 millivolt per second up to 100 millivolt per second. But here we have a much higher scan rate, 50 volt per second. And from figure 5, you can see pure CNT, the bottom curve, the diamond-shaped curve. You can see it has a minimal capacitance. So this capacitance actually is the stack capacitance, not the footprint area. We use volume for this case. And you can see for the pure RGO, is much higher than pure CNT at a different scan rate. But at a higher scan rate, 50 volt per second, RGO and CNT both have pretty bad performance. But once you add RGO with CNT, what happens is if you have pure RGO, those RGO will restack. So you basically lose the surface area. Even theoretically, the surface area of graphene is very high, 2,630 meters square per gram. But in reality, those RGO reduced graphene oxide will restack together. So you don't really have the 2D material advantage. And if you add CNT into this composite, CNT plays 2 roles because, first of all, CNT can open up the RGO. So you keep the distance between the 2 RGOs, for example, then you keep the RGO without restacking. And CNT can also play another role by just improve the electron transfer. Because the good performance for reduced graphene oxide, the electrical performance is on the same plan, but it's not cross different graphene plans. So by adding the CNT as a wire, so you can really improve the kinetics between the RGO layers. So you can see the best performance for our case is 10% CNT with the RGO 90%. We have the best performance, no matter from the lower scan rate, 10 volt per second, all the way to 50 volt per second. We still have really good performance. And not like pure RGO or pure CNT at high scan rate. The capacitance is almost like nothing, less than 1 Farad per cubic centimeter, but here we have still maintain almost 4 Faraday per cubic centimeter at 50 volt per second scan rate. So that's very good performance. And if you look at the charge discharge curve, you can compare, and you can try to draw the Ragon curve to identify the specific power and specific energy. And you can see from the Ragon curve, the RGO CNT 10% CNT ratio give the best performance in terms of both energy and the power. And from the impedance measurement, we can also try to identify the time constant, basically at a 45 phase angle, 45 degree, you can measure the frequency. In that case, we found out for the RGO CNT composite, the time constant, basically that can tell you how fast is the charge transfer, we reached to about 4 milliseconds. So compared to typical thin film capacitors, we have much better performance. The reason is, first of all, we are making the micro electrode. So the distance between the electrode are very short. So the diffusion length, the path is short. So that's the first reason. Second reason is this RGO CNT has a really good performance, not only in terms of the energy density, but it's a very fast response. And even from the first cycle, we don't have degradation for the RGO CNT composite materials. But for the pure RGO materials, usually first 50 to even up to 100 cycle, typically you see the activation process because the electrolyte ion has to squeeze into those RGO materials. So if you want to know more about this research, you can look at our reference papers on 2012 advanced function materials. So basically for Majid's work, his work is based on commercial graphene. So the commercial graphene has an issue. So we have other students follow this work and make different sensors, capacitors, and even battery and capacitor hybrid systems. But we found out from the batch to batch, the graphene quality are very different, and also different company they are selling graphene. We bought different graphene products, but the performance are not repeatable. So we look at the graphene issue for a while. So around 2018, 2019, we have 2 PhD students working on basically exfoliation graphene and making our own high quality graphene. So the motivation is, first of all, from our own setup, our own device, we don't have a repeatability. We see this issue. And we also found that there's a paper by Colin at Advanced Materials about 2018, just about the same time when we realized the quality issue for graphene products. He basically reported a study. He compared about 50 companies, all selling graphenes. They claim they're selling graphenes. He did, materials characterization. He found out only 1 company has a graphene contents, really 2D materials. The graphene contents is from about 40 to 50%. So that means another half of a graphene is not graphene, they are nanoplatelets. And the majority companies, some companies, 9 companies, claim they are selling graphene, they only have like 2% graphene contents. And the majority companies have less than 30% graphene contents, even they say they're selling graphene. So we have to solve this problem if we want to integrate graphene on our micropillar arrays carbon lamps. We need 2D materials. We don't need the nanoplatelets. So we look at the literatures. what process can be, integratable to the semiconductor process. Because typically the commercial graphene products can be produced by either chemical exfoliation or electrochemical exfoliation. But when we look at the literature, there's one group from Dr. Anis Alagui. He did the graphene synthesis by bipolar electrochemistry. So we look at this setup, it's very simple. He used the DI water and put a graphite rod inside the DI water cell and have 2 feeding electrodes from the stainless steel. And he added just outside the electric field through this feeding electrode. Then he can generate bipolar effect. And this bipolar effect, if the condition is right, you can exfoliate graphite into the graphene. But this graphene, what he found out, can only be deposited on the anode side. So it's a positive feeding electrode. And this graphene, if he did Raman and CV, he found out this graphene is actually not that high quality. He has to use a high temperature to further reduce the graphene. Then you can see from the CV, without further high temperature treatment, the RGO, although he claims it's RGO, it's not really highly reduced. So it's like just graphene oxide. So he has to reduce it by high temperature process. So we look at this system, we talk to students, and we talk to Anis, we discuss about how to further improve this. So basically my student modified the basic bipolar electrochemistry. We break the graphite to 2 pieces, and we can connect the 2 pieces of graphite, those are bipolar electrode, with a current meter. We can monitor the total current, we can monitor the bipolar current, we can monitor the solution current, then we can try to understand the mechanism even. And another thing is we found out by looking at the negative feeding electrode carefully, we actually have the vertical aligned graphene deposit on the negative feeding electrode. The reason is when you add, for example, in our case, 45 volt into this bipolar cell, the distance between the 2 feeding electrode is 9 centimeters. So the field is about 5 volt per centimeter. So if you change the distance between the graphite and the feeding electrode, eventually you tune the distance, you will find a good condition. You can exfoliate the graphite from the both bipolar electrode. And at the edge, if this bipolar effect is big enough, basically the water decomposition will generate bubbles. So you have the oxygen, hydrogen at both sides. Those bubbles will be drawn to the graphite, and they can exfoliate graphite. And the ions can be integrated into the graphite at the extreme edge, both edges just near the feeding electrode. Then you can start the exfoliation. Then once the graphene is exfoliated from the graphite, this feeding electrode, just like the electrophoresis, will drive those graphene in the solution. And this solution is DI water. You don't need any chemicals, not like the electrochemical exfoliation or chemical exfoliation. People use harsh chemicals. Here we just use DI water. We can achieve graphite exfoliation into the graphene. And at the negative feeding electrode, we even have reduced graphene oxide compared to the graphene deposit on the positive feeding electrode. Those are mainly layer by layer self-assembly. You can see the correct here shows this pretty thick layer already deposited on the positive feeding electrode. But at the negative feeding electrode, it's graphene, reduced graphene oxide, and it's vertically aligned. So we have more surface area in this case. So we did a lot of research on material characterization and the electrochemical characterization of this BP-based graphene. And we found out this graphene has a much better quality compared to other graphene, since it's really fresh. It's in situ, you can do exfoliation, deposition, and even reduction at a different set of the feeding electrode. We found out for 3D, the high surface area graphene vertical aligned on the negative electrode. As a supercapacitor, we found out the performance is much, much higher than the graphene, which is a graphene oxide deposit on positive feeding electrode. So the reduced graphene oxide with its unique morphology can give much better performance. And the application for this is we try to even use negative feeding electrode based capacitor to replace a commercial aluminum electrolytic capacitor, which is very big. We made a small microcapacitor, and we can just replace a bulky commercial electrolytic capacitor to achieve same filtering effect. So here we are basically filtering out AC signal to create a DC signal. So filter is, very important. Before this work, usually people, all these commercial products, they use AEC, the aluminum-based electrolytic capacitor, because it has supports pretty good capacitance, energy density, and also it's very fast. So you can filtering out the AC signal. But for our electrolytic our supercapacitor is based on the micro array, we can easily replace a bulky commercial capacitor using the electrochemical capacitor. So this electrochemical capacitor has really good application in as a filter. And we have other work trying to understand the performance of this micro capacitor based on bipolar electrochemistry. And you can see some of the results compared to gold electrode. We create the interdigital array. It's a two-dimensional system, but with very high surface areas. You can see from the capacitance, from the phase angle, from the even the area capacitance, we see the dramatic increase of performance using our RGO based microcapacitor. And we also did some modeling work trying to understand from another concept, fractional capacitor concept. We try to quantify how good is the value of our RGO-based capacitor compared to either gold electrode-based capacitor, because that has a really almost perfect 90 degree. So our capacitor is pretty good, and the capacitance is much higher than the gold, because gold doesn't have enough surface area. You can see the capacitance is almost zero at different frequencies. But for the RGO-based microcapacitors, even at very high frequency, we still can maintain high capacitance. So that's one of the best microcapacitors we have. And this is just a circuit, the AC, the circuit how to filter in AC signal and create a DC signal. So we basically replace this bulky capacitor. And another work, I just give you a quick summary. This is another student, Richard Agua. She graduated, now she's in IBM. Her work is a battery capacitor hybridization. So the goal for this work is, if you have a pure double layer capacitor, usually the total energy density compared to battery is still low. It's almost 100 times lower, right? But if we want to make a high energy capacitor without reducing the power density, so my group was trying to make the battery capacitor hybridization. We make the C-MEMS array, for example. This is Ebenezer's work. Now he's in Intel Corporation. His work is miniaturize the carbon MEMS-based battery lithium-ion capacitor. So you can see he has a bare carbon electrode and another pair electrode for the battery electrode is a lithium-ion phosphide. That's a very good battery cathode material. We also have a different setup, like a magnesium oxide-based capacitor materials. We have a symmetric capacitor. We have a symmetric capacitor too. For example, Richard worked on active carbon paired with magnesium oxide and the CNT composite. We try to understand how to optimize, how to match the two materials have very different properties, because for the battery materials, we have a high energy, but at the meantime, the charge storage is either intercalation or conversion mechanism, or some materials have the alloying mechanism. But for the double layer capacitor side, so the double layer capacitor can only store the charge at the interface. So how to match these two different mechanisms from the different voltage window, different kinetics, different charge transfer capability, and the different capacity, how to create a balanced system. So we put a lot of effort on trying to balance the two electrodes. And you can see from this spider chart, you can see typically when we compare asymmetric and symmetric supercapacitors, in this case, we also compare with AC typical capacitors. We found out, the asymmetric system actually can give you much balanced effect compared to symmetric system. But for symmetric system, in terms of AC, the cyclability is the best. But compared to, let's say, energy density, power density, the symmetric AC system, or even symmetric just pseudocapacitor setup, the energy density is much lower than the asymmetric system. So you can see we summarize all these different generations battery capacitor hybrid system into this Ragon chart. We were pushing to the upper right hand corner. Basically, we want to increase both power density and the energy density. So for different generations from our group, we have the carbon MEMS based system. We have a carbon MEMS coated with a magnesium oxide microelectrode. We also have the thin film setup. We compare all this work, we found out our performance can be maintained and as a comparable with a good supercapacitor, but we can further increase the energy density. So those are very difficult work, because the students have to develop their processing, integrate different materials on the microstructures, and do the whole system. So typically this work takes a long time. So for two PhD students working on this concept. So another research I want to quickly summarize is not only on chip level capacitor based on C-MEMS is our focus. We also work on silicon-based on chip supercapacitors. So I work with Intel entire lab is Hill wafer polysilicon-based on-chip supercapacitors. So what we did is we use white etching approach to create polysilicons. And these polysilicons can be 4-inch up to 6-inch Hill wafer. So it's very uniform. And we can coat this polysilicon using ALD coated with either carbon or tin nitride, aluminum nitride. ALD is another powerful approach, can do the uniform coating at a very low pressure. So we can coat this polysilicon. The reason why we coat it is freshly created polysilicon is not that stable. So the surface is very easy to be oxidized. So when you have a coating, you can maintain the stable surface and high surface area. So the goal here is trying to develop a process for conformal coating of different materials like tin nitride into this Hill wafer polysilicon. Then we have 2 wafers. We assemble on-chip capacitor. And hopefully in the future, people can just build the CMOS directly on those polysilicon wafers. So you can see we are pushing the performance from this Ragon curve. All these curves like showing you different conditions, different materials, like carbon coated or tin nitride coated polysilicon compared to bare polysilicon in green color. So coated materials actually has a much better performance. You can see the tin nitride on silicon, polysilicon, which different conditions we can push it further. So compared to lithium-ion batteries, we have a much higher power density, but the energy density is still low. But it's almost equivalent to the thin film battery in this case. So that's a very promising result because we are pushing to the Hill wafer process. So we are now only working on the silicon or carbon MEMS. We also need to develop new electrolyte. So in most cases, no matter it's a supercapacitor or micro battery or lithium-ion capacitor, in our previous efforts, we use liquid electrolyte. Some of the research we use ionic liquid or gel polymer electrolyte, but we realize that we also need to have a patentable solid electrolyte. So the effort with collaborating with Bruce Dunn after I come back from my first sabbatical, we were developing photoresist-based patentable electrolyte. So this is the solid electrolyte. Maybe we can call it a semi-solid electrolyte, but it has a performance almost equivalent to the commercial separator and the commercial solid electrolyte. So we were able to create this modified photoresist electrolyte, have a very broad potential window. And when we assemble a battery using this modified SU8 electrolyte, we compare it to CGAD separator. It has a very similar performance. So that's another effort. But I will just skip all this other work, maybe not truly relevant to carbon MEMS community, but you can see our efforts is beyond just building carbon MEMS and integrate materials on the carbon MEMS. We also work on different other areas. For example, we develop our own high performance battery materials, and we try to understand, for example, in this slide, the memory effect of different commercial capacitors. And we also work on creating fractional order capacitors to trying to tune the frequency response of those capacitors. So those are ongoing works. So we are moving from the pure CMEMS-based setup to different dimensions already in our research group. We use the carbon MEMS for electrochemical biosensors. Dr. Nazib Pala will address that aspect in his talk. And we use the same capacitor not only for the just pure energy storage and the power generation purpose. We have been developing different applications for those microcapacitors. The fraction order EDLC in this case is one of the example ongoing work. We are trying to even tune the solid electrolyte in this case, hopefully my next student can take over this work, deliver good results. So I just want to summarize our C-MEMS work. The carbon MEMS work in our group is mainly focused on chip level energy storage and power generation. We also work on biosensing. We try to develop a different approach, like we use electrostatic static deposition approach, electrophoresis deposition, electrochemical deposition, bipolar electrochemistry, all the different approach try to integrate functional nanomaterials with better performance onto those carbon MEMS platform to create microelectrode. So my groups here, you can see different generation students. They are FIU students. I didn't include my students yet. Hopefully, very soon we can deliver results from my new group. So we have funding source from NSF, DARPA, ACS, Air Force in the past, and I want to acknowledge FIU Emory and the SESMAC faculty and the students really help us. We use the Emory clean room, lot of material characterization, Raman, SRD have been done in SESMAC facility. Now we are moving to Hopefully we have more results can be delivered in the very short term. Thank you, everyone.
That was a wonderful talk, Peggy. It was very informative. Thank you so much. And if anybody has any questions, the floor is open for questions, comments, discussions. Please go ahead and direct your questions. Unmute yourself, please, and then direct your questions to Dr. Wang. Or put the questions in chat, that's also fine.